Hello, welcome again to another practice problem. We're going to do problem 4.13. This problem statement reads, the beam AB is shown as it's supported by the tie rod 1 attached at B and C with double shear pin connections, while the pin at A is attached with single shear connections. The pins at A, B, and C each have ultimate shear strength of 54 KSI. The tie rod 1 has a yield strength of 36 KSI. A concentrated load of P equals 16 kips is applied to the beam as shown. A factor of safety of 3.0 or 3.0 is required for all components. So we need to find the minimum diameter for the tie rod, the double shear pins at B and C, and the minimum diameter for the single shear pin at A. So first thing that I'll do is draw a free body diagram. So we have the beam, right, AB, with a load here, P, that is acting 4 feet from that side and 8 feet from this side. We also have reactions. I'm going to say reaction AY, and then I want to mention also that if you look at this B, look at right here, right? So it's 10 inches above the center line, okay? 10 inches above point A. So that's, we'll just mark here as 10 inches, right? And then we'll have our force here, F, okay? And then we'll have, because F is acting, we'll say to the right, then I'm just going to say that our reaction, RAX, is going to oppose that, just logically. RAX is going to go to the left. So now that we have our free body diagram drawn, I'm going to say that we're going to solve for the forces, right? We have 3 unknowns here, well 4 technically, because we have our degree measurement here, theta, right? So we don't know this angle that F is acting at, but we do know that it's acting 10 inches above point A. So we have 3 unknowns that we need to solve for, and this should be at this point a review of statics. There's a problem that I did in a video 1.30, and I stepped through all the steps on how to solve for the exterior reactions. In this case, what I've done is I already solved for it, so we're just going to go ahead and walk through it. What I did is solved for using trig, solved for our theta that F is acting at. And then I used our 3 equations because we had 3 unknowns. And with these 3 equations, you have to use, substitution methods to be able to solve for the forces and the unknowns. And once I did that and substitute in, I got a force F is 16.8 kips. And then I got the components, right, of A and Y. But we're not looking for just the components. We need the magnitude of the force acting at A. And so the magnitude of the force, I did the square root of the sum of the squares, and I got the force at A equaling 15.086 kips. So now that we know the forces acting at tie rod 1 and the force acting at A, what we can do now is look at what the problem was actually saying. So in chapter 4, we're talking about a factor of safety. So a factor of safety, right, we'll write factor of safety is going to equal our stress at failure divided by our stress allowable. Now think about this logically. If we want a factor of safety to be larger than 1, right, then the value that we have up here in the numerator has to be larger than the value that we have down here in the denominator, right? So this is smaller. Okay, so what we know is, given in the problem statement, that the ultimate shear strength, the pins A, B, and C have an ultimate shear strength of 54 KSI. The tie rod are a yield strength of 36 KSI. So we'll say the pins, right? So the pins, right? We'll say algebraically solving this for our stress allowable is going to equal our stress at failure divided by our factor of safety. So for the pins, our stress allowable is going to equal our 54 KSI divided by our factor of safety, which is stated in the problem statement that the factor of safety for all components is 3. So 3.0. So 54 divided by 3, you get 18. So our stress allowable for all pins is going to be 18 KSI. Okay? And so for our tie rod, same steps, just a different failure stress. So stress allow is going to equal our 36 KSI divided by 3, 12 KSI. Okay, so now what we can do is, because we go back to what we learned in chapter 1, right? In chapter 1, stress equals force over area, right? So we're looking for diameter, minimum diameter required to be able to support this beam under these loading conditions, right? So we have, I'm going to scoot over to here. We have our force at A, right? Our force in the tie rod, and then we have the allowable stresses for each. The pins, right? So this is pins, and this is the tie rod, right? So first, let's do our pins at B and C, okay? Pins at B and C, you know, it's stress equals force over area. Solving for area, it's then area equals force over stress. And we know the force is going to be 16.8062 kips. So area equals 16.8062 kips divided by our 18 KSI, right? 18, 18, and this is kips per square inch. I'll write it like that so we can see our units divide out. 16.8062 divided by 18 equals, I got our area equals 0.933683 inches squared. So for the pins B and C, right, the formula for the area is going to be pi over 4 diameter squared equals 0.933683 inches squared. But we need to remember that the pins at B and C are double shear connections, right? So that means that we need to multiply this to 2. Okay? So what you can then solve for is diameter equals the square root of 2 over pi multiplied to 0.933683 inches squared. So, and I get a diameter of, for both pins at B and C, the diameter is 0.77097 inches. Okay. So those are the pins at B and C. So let's do the pin at A, right? So it's the same process, but instead of it being double shear, pin at A is single shear. So pin A, same process. We have this equals force over area, area equals force over stress. And so our area then equals, in this case, the force isn't our 16, it's 15, right? So the magnitude of the components at point A, so 15.0861 kips divided by the stress at pin A. So 15.0861 divided by 18